Okay, so I'd like to start the second lecture on physical metallurgy of zirconium alloys by introducing and telling you the topics I'm going to be covered, which is texture, elasticity, deformation mechanisms, principally the plastic deformation mechanisms, and I'm going to finish off by introducing a parameter which is called the Kearns texture parameter, which is related to the texture, of course. So texture, what do we mean by texture? In the top here, you can see I've drawn schematic diagram of a tube, and in it I've shown typically how that tube material may be constituted of a collection of grains which are all joined together by grain boundaries. So each grain in effect is a separate crystal of zirconium or a zirconium alloy, and these crystals have differing orientations. Now, because zirconium, the crystal, is anisotropic in its properties, the collection and the distribution of the orientation of these crystal orientations in different grains has an impact on the collective macroscopic properties of the component, in this case a tube. So it's important often to know what the distribution of the crystal orientations are in a material, and we use X-ray diffraction, not specifically X-ray diffraction, but X-ray diffraction is a common way of measuring the texture. So what you're interested in is the volume fraction of grains which have a particular orientation. Now, the most common pole that one uses to define the distribution of orientations of the grains is the basal pole, shown here, which is basically the direction perpendicular to the basal plane in the hexagonal crystal. We could look at other poles, like the planes or directions which are perpendicular to prism planes, for instance. But in this instance, we're going to be considering the basal planes. And what we do is that we reflect X-rays or electrons or some other scattering probe off planes at particular orientations, and so we can determine the intensity from the intensity of the diffraction, what volume fraction of the grains sit in a particular orientation. And we define the orientation by alpha phi here, so that if we put this onto a three-dimensional grid, we would apply a point, a value to a grid element given by alpha phi, which defines this orientation, and that would then be proportional to the volume fraction. Obviously, we would want to normalize over the whole of the material, but we get a value for a distribution of values over these grid elements which are proportional to the volume fraction of grains with a particular orientation relative to that grid element, as shown here. For a component that might be a pressure tube or a fuel cladding, a fuel pin or fuel rod, I've shown an example here of how this is often displayed. So although we may pick up, if we represent the intensities of the volume fraction of the different grains in terms of a contour map, green here being high values and blue being lower values, and basically no values here. What this schematically shows is that for this particular idealized system or component, we have a very high probability that grains with their z-axis are oriented in the transverse direction. it's a distribution around the transverse direction, but we can basically plot this either on a stereogram, essentially a three-dimensional grid, or we can project that grid onto a flat surface, which is the stereographic projection. And so typically one would see a pole figure as a stereographic projection. And what this shows is that there's very few basal poles, or very few grains which have their c-axis in the radial direction. There's nothing there, but many grains are oriented in a closer to the transverse direction. The peak perhaps is slightly between the transverse and the radial direction in the radial transverse plane. So this is typical of many tubular zirconium alloy components. And this is for a pressure tube, and what it tells us is that in this particular instance, that most of the c-axes are oriented close to the transverse direction. Now, with the advent of electron backscattered diffraction, texture information has become much more valuable, much more interesting. There is much more interesting information that can be determined using EBSD, which is a microscopic probe into the orientation of the grains. Just as I showed earlier with the pole figure, how there are a collection of grains with different orientations. The pole figure here, start with the basal pole figure, shows the essentially how many grains, or each point is some value that gives you, tells you that you can relate to a grain. So each grain in this area that's studied here shows up as a point here on the pole figure. We haven't normalized them for the volume fraction because some grains might be big and some grains might be small, but it gives you an idea of the distribution of the grains in this particular instance without going into any quantitative information about the volume fraction of grains with a different orientation. And what this shows is that in this projection now, we're looking down the longitudinal axis of a tube. In this projection, many of the grains appear in a more or less equiaxed shape when they have their c-axis oriented in the radial direction. So this is the radial direction here. So these green and blue grains correspond with this region of the pole figure. And the red grains are out towards the transverse direction, which are more like this direction. So the green and blue look like, are oriented a bit like this, and the red are oriented a little bit like this. So just as an aside, if you notice, the green and blue are, even though they share a common basal pole orientation, they are kind of separated when it comes to prism poles. And what that shows is that the one is rotated with respect to the other, and the typical rotation here is about 30 degrees. And that's what happens when the material recrystallizes. So with respect to either grain, the blue, purple ones or the green ones, one of them is recrystallized with respect to the other. And I think it's the green one in this particular instance. So we have a cold work grain which has this orientation, and when it recrystallizes, it rotates about the c-axis and gives you this rotation difference, but the c-axis is still more or less up in the radial direction. As I mentioned earlier, the thing with textures is the distribution of the orientation of the grains has an effect on the properties, the macroscopic properties of the component. We're often dealing with tubes, whether it be guide tubes, fuel cladding rods or pressure tubes, and this is an example of some of the types of textures one might get. We might have a prominent radial texture, which is typical in a lot of fuel cladding, either in this orientation or this orientation. Or you might have a texture like this, which is typical of thicker pressure tubes. And the texture you get depends on the thermomechanical processing. If we're talking about tubes, the extrusion properties. So by and large, if you have a high extrusion ratio, the ratio of the wall thickness before and after extrusion is very high, you end up with or should I say, the cross-sectional area of the end of the tube is relative to the cross-sectional area of the end of the tube at the end of the extrusion is very high, then you tend to get this standard texture up here. For plate materials or tube reduction, pilgering type operations, you tend to get textures more like this. So fuel cladding gives you more like this texture. Extrusion of pressure tubes gives you more like this texture. So I've mentioned how the macroscopic properties are dependent on the distribution of the orientation of the crystals, and that is because the crystal itself has an anisotropic properties. This shows the the Young's modulus or elastic modulus for different hexagonal close-packed materials, and here is zirconium. And what this shows is that perpendicular to the C-axis up here, the material is strong, elastically strong. The displacement you would get by the imposition of a tensile stress on the C-axis is relatively small in that case, because it's stronger in that direction. It doesn't deform as easily. Whereas in the prism direction, it's much softer. And for that reason, when you have a very pronounced texture, as we do here in a pressure tube material, for instance, what that means is that if we're to look at the elastic modulus in a direction parallel with the transverse direction, we have a high elastic modulus of the polycrystal and a low elastic modulus of the polycrystal in directions closer to the radial direction. Another physical property which is determined by the single crystal physical properties is thermal expansion. Here's some data on the thermal expansion of single crystal material, and what you see is that in the C-axis, the thermal expansion coefficient, that is the degree to which the material strains when it's subjected to temperature increase or decrease, is higher in the C direction compared to the A direction. As we increase in temperature, at some point the material for zirconium becomes it's an allotropic transformation to the body-centered cubic, and that has a thermal expansion coefficient which is closer to the C-axis. So what is this? One of the things that happens when you have an agglomeration of different grains of different orientations, when you subject them to mechanical mechanical treatments, impose stresses on them, induce a strain, either mechanically or from irradiation, or if we simply heat them up and cool them down, we get we'll have a different response depending on the orientation of the different crystals. So if we consider two crystals which are both joined along a grain boundary, what happens when we change the different conditions that are imposed on the component. So if one was to compress, look at compression. When you compress, in the case of the prism directions, the prism poles, the material deforms easier than it does if you're compressing along the c-axis, just the way it is, and I can explain more about that when we go into the details of mechanical processing. So what happens is that you get this component, this grain would deform easier and therefore higher strain compared to this grain, and that results in incompatibilities. Now, how the material deals with that is that because it can't, you have to have integrity of the material unless it's going to crack. If you get to the point where the stress is so high or the material is so high that you create a discontinuity between the two materials, unless you've got that, what you end up with are differences in the stresses that exist in the different grains. And so because this grain has plastically deformed more than this grain, but it still has to be joined to this grain, and because this grain has plastically deformed less than this grain, but it still has to be joined, the two maintain their compatibility by having different elastic stresses, so that the length of this contact region is the same by having different elastic stresses. Same thing happens if you're heating and cooling. So if you equilibrate the material by sitting it at a high temperature and then you cool it down, and let's say that there's zero stress at a high temperature because it's relaxed, it's because of creep at a high temperature, and now we cool it, what would happen is because this grain shrinks more than this grain, you end up having a tensile stress in this direction for this grain and a compressive stress in this direction for this grain. Same kind of thing happens with the radiation. When you look at the radiation of zirconium, the simplest way to think about it is that the material contracts along the c-axis and expands along the a-axis, and because of that differences in the way that the material responds to radiation, you get a mismatch, a strain mismatch, which again would be accommodated by some elastic differences in the elastic strain. Okay, I said that we'd go on to deformation mechanisms, so let's consider those. Plastic deformation in this particular case compared to the elastic effects we were just talking about. There are two main ways in which a material can deform. It can either shear along a slip plane. Let's say this is an arrangement of atoms, and we can shear this block of atoms like this on particular planes, shear them on different slip planes like that, or we can shear rather than just in one plane, we can shear as a bulk shear operation, and that's known as twinning. So we can take a lattice like this and shear every layer the same, displace it in this direction, and that produces that kind of bulk shear, produce a twin, or we can have the planar shear. There is one other form of plastic deformation, which is the martensitic shear. In that particular case, you can have alternating shear on alternating planes with respect to the epsilon martensite transformation that occurs in zirconium. Now, in a live presentation, I'd be demonstrating these processes, the shearing operations with the ball models. I showed dislocation slip and also the various twinning and martensitic operations. Can't do that easily with this presentation, recording it, so I'll leave people to look at the YouTube videos I've embedded in the presentation package. So when a material shears, it does so by creation of dislocations. And the type of dislocations you get in zirconium alloys are dependent on the shear plane and the shear direction. So if your shear direction is inclined to the basal plane, it's like you want to deform, either elongate or compress along the C-axis, you get one type of dislocation, which is called a C-component dislocations. Typically it's C+A type dislocations. But if you deform perpendicular to the C-axis, within the basal plane, you get a different type of dislocation produced, and these are caused by slip on these prism planes, as opposed to slip on what's called the pyramidal planes, and I'll talk a bit about that in a minute. And the two types of dislocations are most easily illustrated by using a basal pole diffraction vector. In the one case, we have a C component, and they show up as dark lines. And in the A-type dislocations, we have no C component, and they don't show up at all when you image with a basal reflection. So what do we mean by, what am I talking about? I guess I could have introduced this earlier, but it's difficult to put everything in all at once. In the hexagonal crystal, we have different planes, which are planes of certain density of atoms. And these then dictate, if you watch the videos, how the material will slip depending on the direction and the plane at which it will slip. Now, if we look at the basal plane, which is this plane here, slip occurs by two partials, and this is essentially very similar to what happens in a face-centered cubic material. And what you get is slip occurring by a dual glide process, which involves two partials, and I'll demonstrate that. If you watch the videos, you'll see what I mean by that. When you see it with the ball models, it's most easily demonstrated with the ball models. And I can also illustrate it in the next couple of slides, just show you what I mean schematically. So this shear operation on the basal plane is very similar to what happens in FCC. In FCC, these partials would be basically the Shockley partials, what's known as the Shockley partials, and that is 1611 bar 2, and here the partials, which are equivalent to the Shockley partials, are a half 10 bar 10 type. Interesting feature of slip in zirconium, if you're slipping in the A direction, let's say the A2 direction here, if you're slipping on other planes, these intermediate positions that you get that are equivalent to an FCC don't exist. This is in particular for the pyramidal plane. The pyramidal plane is this one, which is inclined to the basal plane, and it is not one of the prism planes. So my old supervisor, well, one of my old supervisors at Birmingham University did put together this sketch to show and calculated what the displacements are, the perpendicular displacements when one glides one plane over the other. And because the planes in zirconium are corrugated, what we end up with is a whole range of different possibilities in terms of slip operations. And again, the best way to illustrate this is using the ball models. And if you check on the videos, you'll see exactly what I mean when we look at these different configurations. So I said there's two types of dislocations. We use TEM to image them. And here's a zircaloy or zirconium niobium pressure tube. When imaging with one conditions, the 1,1 bar 2, one sees all types of dislocations, and the contrast is kind of pretty poor. But if you image with a basal reflection, you only see dislocations of a particular type, C+A in this particular case. And what's interesting about the A and the C+A dislocations is that they're slipping on different, gliding on different planes. So if we look at the glide of an A dislocation on this plane and a C+A dislocation on a pyramidal plane, when they interact, they can interact and they can form a low energy dislocation and a junction. And that junction very often is sessile. So you end up locking in a dislocation structure when you get slip on both planes. So I'm going to revert a little bit to the FCC case in order to illustrate, to make the transition now between slip and twinning. Although I've shown you it in the video, if you watch the videos, here it is schematically what is the difference between slip and twinning. Now in an FCC case, the slip involves taking one atom here, displacing it. It would sit in an interim lower energy site here, and then a second displacement by a second Shockley partial puts it into an equivalent lattice position. So by the time you've done that and that, the material doesn't know it's being deformed. It's imperfect. It's a perfect crystal. However, if you move this atom and sit it there, you end up with a stacking fault because you've actually created a C layer, and the material is aware that it's been that you've had a shear on one plane. However, okay, so I mean that's just slip, and again, it's best to illustrate with the ball models. What's twinning? Well, twinning in the case of FCC involves this first shear on one plane, but then the next shear on the next plane up, and then another shear in the same direction on the next plane up. So what you end up with is 1, 2, 3 shears occurring over a period of 3 planes before the material comes back into register. And what you've done when you do that is you've created a mirror image of the original material. So we've got original material here. This is the bit that's going to get deformed by the twin shear. That is the twin shear. Each twinning operation involves a 1,611 bar 2 type displacement, 1, and then there's 2, and then there's 3, and you end up with a mirror image of the original material. Now, twinning and here's the mirror image here. This is by some French guys, Bleikampf and et al. I forgot to put the reference here, but anyway, this shows the orientation, if you look at it in terms of a ball model, of a twin structure relative to the original matrix structure. And there's some relationship between these planes. Sometimes it's a little bit odd. For instance, what would have been equivalent of a 111 plane in the parent material is actually a 511 plane in the twin, if you think about the same orientations and or equivalent orientations, like this face here. Okay, sorry, it would still be, sorry, I should have corrected myself here. That 511 here refers to what this 1-1-1 plane in the twin is, it's 1-1-1 plane in the twin, it's parallel with the 5-1-1 plane in the twin, in the original matrix. Excuse me for mixing up my terminology there. But basically, when you twin, you end up back at the original structure, but it's changed in the orientation. And the orientation is such that the main close pack planes in the twin are parallel with different planes, in this case the 5-1-1 plane, in the parent matrix. Okay, so one of the things that's commonly quoted is the shear that's caused by a twin operation. And what do I mean by shear? Now, for those of you familiar with tensors, you'll know that the strain of a given in a given material can be represented by a strain tensor, and that relates the displacement in each of three, or in this case orthogonal directions, with the position of let's say an atom. So we have a displacement relative to a position. So if we have an atom which is in position x1, x2, x3, or just x1, it can be related to a displacement by this matrix, which is the strain tensor. So one of the elements of this matrix, E12 for instance, represents a shear strain. So what that means is the displacement in a given direction, in the x1 direction, relative to the plane given by the x2 direction. And the shear is simply the displacement in one direction divided by the spacing of the plane. And so the shear in this particular instance, if we're talking about a single shear operation, because we're dealing with each 6-1-1 bar 2 corresponding to each 1/3 1-1 bar 2, so you go along this amount for each spacing, which is given by this value, 1/3 1-1-1, and that is the shear strain. So again, it's just a little bit simpler perhaps to look at, to summarize. For an FCC structure, if we consider the C layer here, for instance, and we want to displace the C layer, it will glide over the B layer here in this direction. This green atom in this C layer can move in this direction in a partial, and then it will be sitting directly over the blue atom in the A layer. And then when it moves again in a different partial, the sum of the two is a perfect dislocation, which is half 1/1. It brings the lattice back into register. So you go via this, from this site to this site to this site. And again, using the ball models, it's easily demonstrated, and it's easy to see this as opposed to this projection. The difference between the slip on a plane and twinning is that if we consider this partial, what twinning is that you move each layer by the same partial amount. So the green one goes this amount, the blue one goes this amount, the red one goes this amount. And that total shear in this case is half 1-1 bar 2. And it occurs over 3 layers of atoms, and that essentially it can keep going, and the twin can grow. So this is a bulk transformation, whereas this is a planar transformation. Enough of the FCC. What is the equivalent situation for a HCP for zirconium? Well, one of the things that can happen apart from twinning in FCC is that shear can happen on alternate planes, on every second plane. And if it happens on every second plane, you end up creating a hexagonal close pack phase. And the reverse happens if you start out with a hexagonal close-packed phase. You can actually make an FCC phase by shear on alternate planes. And what do I mean by that? Let's start with an A layer. And if we're talking about slip with respect to this A layer, so the next layer is the B layer, and the B layer can shear by this layer of atoms moving in that direction first and then in that direction, and then it brings it back into perfect registry. And that is what happens on the basal plane in zirconium. But now let's think about the next layer up, and we'll show that in green. So the plane above this one, B layer. And if I try and move that layer, that layer in the same direction as the second layer, the B layer would have been, I can't. Basically, it's got to ride up over the atom in its way. There's an atom blocking it from shearing. But the next layer up, the next B layer with respect to the A layer, I can actually shear. And if you shear every B layer, in effect, what you end up with is changing the crystal structure from an ABA stacking to an ABC stacking. So this alternate shearing on every second plane, or every B layer, in the same direction, is known as a Martensitic transformation. But what's more important is that this shows that you can get no twinning on the basal plane in hexagonals, certainly in zirconium. So the next slide shows some possible slip and twinning planes in hexagonal materials. I mentioned earlier that the tendency to slip or twin on particular planes depends on the C/A ratio. So for zirconium, in principle, the primary slip systems are this one, the prism and the pyramidal. This gives you C+A, this pyramidal one, and this gives you A. So these are the two most common dislocations, C+A and A. Likewise, in twinning systems, you can get all different combinations for all hexagonals. But the ones I'll start to show you in this particular case will be this one, twinning on the 1/2 plane and twinning on the 1/1 plane. Some time ago, back in the 60s, this guy Mendelssohn put together a study showing all the possible twinning systems that can occur in hexagonal metals. So that doesn't mean that they're all going to happen in zirconium, but some of them will. And the way to define twinning in hexagonal metals as opposed to FCC is by considering what's called the second undistorted plane. So I show this in the videos, in the presentations with the ball models. So it's very easy to see when you can demonstrate it with the ball model. But for now, I'm going to assume you've seen the presentation, so you know what I mean when you have the second undistorted plane. So the first undistorted plane is the shear plane, but there is always a plane which is inclined to that, which when you make the shear of a partial on each successive plane of these planes, you end up bringing at least one plane into registry. And what I found when I use my ball models is that the second undistorted plane for a 1/1/2 or a 1/1/1 shear is the basal plane. Now, in this table coming from Mendelssohn, the shear directions are given here as 3/0 of shear planes are given by here as 3/0 bar 3/0, and the shear directions by bar 2/023 or bar 1013, and that is because they're not even though this corresponds with the 1/1/0 plane and this corresponds with the 1/1/2 plane, because it's corrugated, the shear operation actually is inclined to the plane. So this is the likely shear on 1/1/2 because it gives a rational partial, which is this one. And this is the shear on 1/1 because it also gives a rational partial, this one. And again, if you see the videos, you'll see what I mean by that. I can try and demonstrate that in this case using this model. Here we're looking down planes of atoms. We're looking at the A layers, looking along the 1,1 bar 210 direction, and the black atoms denote the A layer, and the clear ones the B layer, and these pairs of lines here denote the planes. Now, as I said, the planes in hexagonals which are non-basal are actually corrugated, and that means that one has this kind of zigzag kind of structure to the planes. So for the two twinning operations I described, the first one of the ones, which is for the 1/2 plane, involves shearing up in this direction. So we go from here, or from here to here, from here. So because this is now on, we've already had this shear going on, and then we add to it this shear, and then we add to it this shear. And what that does, it brings these atoms, it creates a plane of atoms here, which is a new basal plane. It has the same spacing and the same arrangement as this plane. So what you're doing is when you're going from the base material to the twin, you're rotating this plane into this plane, looking down the prism pole 1 bar 210. Likewise, for the 1 bar 10, we're moving these atoms in a specific direction, and then the basal plane is now inclined to what it would have been in the parent material. Schematically, again, a different way of looking at this. Twins are often depicted this way, showing how the basal pole is rotated. In the case of the 1 bar 12 plane, what happens is that the basal plane rotates by about 85 degrees from here to here, and in the 1 bar 1 plane, the basal plane rotates from about 57 degrees from here to here. I'm not going to get into it here, but these shears represented here are not the same as these shears that I calculate with this twinning mechanism. This is kind of an odd way of looking at the twinning by looking at the final product of the twinning operation. Because one of the things I omitted to say is that these shears, and if you'd have seen this with the video of the ball model demonstration, even though this plane would be the second undistorted plane, the first undistorted plane being the shear plane, this other plane, undistorted plane, when you move this plane and rotate it, and you also have a basal plane in the twin, the remaining atoms around that undistorted plane are actually all out of position, and they have to shuffle or collapse in order to bring the whole crystal back into registry. And that is typical of hexagonal metals. You end up with a shear of where one can consider one particular plane which is undistorted, and then the rest of the crystal reforms around this new plane or this reoriented plane. Talk a little bit about slip now. I mentioned C+A slip, and that occurs on these corrugated prism planes, the 1 bar 1 planes, and whether one gets slip on a 1 bar 1 plane, a C+A slip, or whether one gets slip on a prism plane, one of these other planes, depends on the resolution or the shear stress parallel with that plane. And to get the shear stress, one needs to determine what's called a Schmidt factor. And so if we had a simple tensile stress, the actual shear stress in the direction, in this case of the Burgers vector, the direction in which the material can shear, it can't shear in all directions, it can only shear on specific directions depending on what the Burgers vector is possible on that plane. And you resolve this tensile load onto the plane, which is parallel with the slip plane and parallel in the slip plane and parallel with the Burgers vector, which is the allowed direction for slip. So because this plane has a larger area than the normal to a tensile axis, for instance, this force is dispersed over a larger area that reduces the force on this slip plane, and one has to resolve that force also into the Burgers vector, and therefore you end up with two factors which determine what the shear stress is on the plane of interest. And this is actually a simple tensor transformation, and I'll talk a little bit about that, but not too much. So here I've shown a single crystal, and when one determines what the Schmidt factor is, one has to consider the axis system of the plane of interest. We have an allowable direction in which slip can occur, the normal to the plane, and that's just the cross product of these two vectors. But the crystal itself has a different axis system. So if we were to think about shear on a given slip plane, one can define the strain tensor in this way. This is my E12 value and this is my E21 value. So basically what this describes is that there is in this particular instance, you can say that you can have shear in the direction in this case 2, which would be this value, which is perpendicular to the plane defined by the vector given by 1, x1 or x2 or x3 or whatever we want. And for symmetry, I'm just going to conform with convention. There is one can have potentially another shear E in the one direction on the plane perpendicular to 2. In fact, it doesn't exist. So this is kind of a fake representation of the possible shears that one can get. But it applies. The reason I'm putting it here is that it's relevant for transforming stresses, which have to be symmetric. Strains don't have to be, and in fact can't be when you're talking about an FCC structure or a HCP structure. They cannot be symmetric, but this is how it's generally depicted incorrectly. So how you would represent this simple deformation in this particular case is by transforming the axes into the axes that represent the crystal, in this case the 1 or 0 directions. And when you do that, you end up with transforming this strain tensor by these factors, where B and N, B1, B2, B3, and N1, and 2, and 3 are the projections of the unit vectors defined by B and N on this slip system in the single crystal axis system. This is what's known as a Schmidt tensor. As I say, it actually doesn't make any sense when it comes to strain, but it makes a lot of sense when it comes to stress. because stresses are typically symmetric, or have to be symmetric in order to maintain equilibrium, the stress tensor is often represented by this, the stress tensor with respect to a given slip plane. And one can then, if one has a stress state in the single crystal, it turns out that one can use the Schmidt tensor to determine what the shear stress is on the plane of interest by simply taking the inner product of this, what's called the Schmidt tensor, with the applied stress tensor. And this applied stress tensor in the single crystal may be something quite complex. I don't want to go into two more details, but it is explained in various papers. So finally, what does this mean? Ultimately, well, we have different deformation processes that can occur depending on the angle of the basal pole, with the, in this case, a simple tensile axis. So if you're at 90 degrees to the, sorry, if you're at the angle between the direction of stress and the basal pole. So in this particular case, we are perpendicular to the basal pole. Sorry, we were parallel with the basal pole. And in this case, when you're pulling along at c-axis, you get this type of twinning operation. And if you're perpendicular to the basal pole, this is the slip you will get. You get a slip. So perpendicular to the basal plane, you're more likely to get a slip. Parallel to the A direction, sorry, to the C direction, you're likely to get twinning. And if you're 45 degrees to the C axis, in principle, you can get basal slip if it's allowed. Finally, Kearns texture parameter. What is a Kearns texture parameter? Kearns texture parameter is a way of resolving the strain for a single crystal. So for each grain, one can transform the strain in the grain onto the component reference axis. And this tensor transformation, it's a tensor transformation, and I don't have time to go into the details too much, but suffice to say is that if we have a strain tensor, which represents the strain in a given grain, one can determine what the strain is in the direction of a component, say along the axis of a tube, by the use of what's called the Kearns texture factor F. And the F factor is, it's really, if I can define it, it's the volume weighted transformation of the strain of the singular crystal onto a component of interest, onto a component direction of interest. So when it comes to, if we, in this example, what I've shown here is if we have a radiation growth where this is 1, this is 1, this is -2, the growth in the reference direction is given by whatever the single crystal growth strain would be EA E11, for instance, times 1 minus 3F. And F is the factor which is basically this factor. It's the cos squared I, theta I. It's the cos squared of the angle between the basal flow and the direction of interest, weighted by the number of grains which have, or the volume of material which are aligned in this direction. Kearns texture practices, this is the last slide, are very important because they give you a measure of the physical properties of a polycrystalline material. This shows the thermal expansion coefficients of a polycrystal as a function of the F factor. And what this shows is that if we have a very high F factor, basically looking along the mostly grains which are oriented with a C-axis in the direction of interest, if we have a very high F factor, we have a high thermal expansion coefficient, which is basically the single crystal value for the C-axis thermal expansion, and perpendicular to the C-axis we get a low value. And intermediate to that we have a range of possibilities, which is simply the interpolation between these two values. Okay, that's enough. Thank you.